Hello, welcome to this lesson in Mastering Statistics. We're still going down our journey in learning about hypothesis testing. And I've taken you through quite a journey up till now. So I want you to take just a step back here as we start this next major topic in this area. And let's kind of go down memory lane and see where we've gone. Because as we continue this journey, some of what we've done in the past is going to parallel what we're going to be doing in the future. Okay? Ultimately, where we're going to be going is we're going to be doing hypothesis testing that involves, in this lesson, two means. Okay? All of the hypothesis testing we've done in the past has always been involving either one mean or one standard deviation of a population, or one population proportion or something like that. All of the null hypothesis and research hypothesis was just seeing if sigma was greater than 2, or if mu, the mean, was greater than 5 or less than 3. It was just involving one population parameter, and those types of problems are very common, very useful. But as you start to do more statistical analysis, sometimes you have two groups of people, two populations that you really want to compare. And you want to see, for instance, if they're how they're related to each other statistically. And that's going to be a little bit of a fuzzy concept until we get into some actual problems. But I guarantee you, once I read you the very first problem, you'll be able to look at this and say, okay, I understand. I can recognize how something like this would be useful. So just kind of think about it in terms of when we're doing population testing or hypothesis testing with two means, for instance, that we usually have two groups of people that we're comparing. And we're trying to see maybe one's greater than the other, maybe one's less than the other, and we want to see statistically from sampling how we can prove that to be the truth through hypothesis testing. Okay? But before we get to that, let's go down memory lane. Okay? We have done hypothesis testing with means, with population proportions, and with variance standard deviation. And if you remember, when we did it with means, we had large samples and small samples. If we had large samples, we ended up using the normal distribution, because when you have a large number of samples, the normal distribution can be used, and Z was our test statistic, Z. Okay? Then when we were doing means, hypothesis testing with means, with small number of samples, we ended up using the T distribution. It looks bell-shaped, but it depends on the degrees of freedom, because it's a very small number of samples. You can't use a normal distribution. You have to use this other distribution called the T distribution. Then when we moved into the realm of population proportions and hypothesis testing, we also used a normal distribution, but we just had to make sure that the number of samples we had was high enough to use it. And we had some criteria that I showed you to make sure, like n times p is greater than or equal to 5, for instance. And then we have population variance and standard deviation. When we're doing hypothesis testing with those, we had to use a totally different kind of distribution called a chi-square distribution. Now this kind of sequence of events with hypothesis testing, with doing means, small and large samples, and then proportions, and then variance, and all the different ways, and we did that, and sort of the different distributions we used along the way, is going to be very parallel to what we're going to be doing in the next sections. The only difference is we're going to be having two means, or two population proportions, for instance. And until I read you a problem, you won't quite understand why you would ever need two of them, but basically it's comparing two groups of people. Think about shoppers, group of shoppers A and group of shoppers B. Maybe we want to figure out which group of shoppers spends more. So we're not really doing a hypothesis to see, does this group spend more than 10 or does this group spend more than 20? We may just have two groups of people and figure out which one's spending more. Maybe we have the population of men in a city and the population of women in a city, and we want to figure out which one's spending more. Or maybe we're looking at distribution of IQs or distribution of heights or weights, body mass index, something like that. And we have two groups of people. Maybe we have a group of people who was on a diet and a group of people who wasn't on a diet. And we want to figure out, how their average weights or something like that compare to one another. Which one was greater, which one was less. Well, we can't look at everybody in the country, so we have to do some sampling. We take 25 people from group A and 25 people from group B, we do some calculations, and we have a null hypothesis and a research hypothesis, and we want to figure out if we can reject the hypothesis. So it's the same idea, it's just we have two groups of people. Now along those lines, some very important words I want to throw out at you here. I could write them down, but honestly I just think they're kind of simple, so I'll just tell you. All right, there are two things or two definitions that you need to know going forward. One of them is independent samples, and the other one would be dependent samples. Independent samples is exactly what you would say, or exactly what you would think it means. We have two groups of people, for instance, two sets of sample data that are not connected or related at all. Those are called independent samples. So in other words, if I have group 1 over here, and I choose 52 people from group 1 and I study them, calculate some stuff, and then I have group 2, which is 37 group of people, but I don't choose the same people. I go over here and I choose 37 different people. Those people are totally different. Okay? So those are two different groups of people that are independent of one another. So we call it independent samples. It's exactly what you would think. If you really want to do something independent, you choose different people, right? And some problems are going to be aligned into independent samples. So we're going to be having group A and group B. They're going to be different people not connected in any way at all. And there's a technique to handle that, and I'll show you what that is. But the opposite of that would be a dependent samples, right? Those are usually the same people, but the study is done pre and post test, or pre or post event. And the typical thing with that would be like a weight loss drug, right, or something. So you have 35 people that you're going to run through a clinical trial, and you measure their, for a few weeks beforehand, you measure their weight and their diet, and then you start giving them this drug. And then you measure their weight and their diet for like 5 months after, and you see what happens. But see, those 35 people, those are the same people, right? So that's not independent. I mean, you may be able to draw a conclusion from that, but they're definitely not independent because those people are the same people, okay? So that's why we say dependent samples, usually the same people, but usually the study is done before and after whatever it is you're studying. You may take people and you may, see if they get motion sickness. Take the same people, put them on a boat, okay? Or maybe take the same people and do something else to them as far as a clinical trial, a drug, blood work, something like that. If you're using the same people, they are dependent sets of samples. But if you're using different people or different factories or different sampling of totally different piles of things, those are independent samples. So I think that's pretty clear, so I don't think I need to write that down. So in this particular case, we're going to be doing hypothesis testing with two means. I already told you that. I'm going to kind of write that down. We're doing hypothesis testing with two means. And we have a lot of things tacked on to that because we have a couple of different kind of important things to note in this particular section, what we're going to be doing. These are going to be large sample sizes n greater than 30. We always have, for means, we always have large and small. So this is going to be large. These are going to be called independent. So two groups not connected. Two totally different groups of people. We're going to be doing independent sampling. And of course, we already said we're doing two means. Okay? So we're testing a hypothesis about how two population means are related to one another. And because you have two means, remember the symbol for a mean, for a population mean is mu, that squiggly looking U thing, right? But because we have two means in all of these problems, we have to keep it straight which population we're talking about. So the way we do that is we have mean number 1, so we put a sub 1, and this is the population mean 1. And we also have mean number 2, this is the population mean 2. Okay, so this is all about hypothesis testing. I haven't given you a problem yet, but you know that it's going to be involving two means, not just one. All right, but the basic idea is going to be the same. We're going to formulate a hypothesis, a null hypothesis. We're going to write the opposite of that, which will be the alternate or the research hypothesis. Okay, then we're going to have to draw a little sketch, and then you can either use rejection regions based on your level of significance, or you can use p-values, and ultimately you're going to calculate a test statistic and figure out if you reject this null hypothesis or not. Now, usually, because we're doing large number of samples, just like before, large number of samples with a mean, we're allowed to use a normal distribution. So in these types of problems, we're also going to be allowed to use the normal distribution. So because we're using the normal distribution, you have the option of using the rejection regions, but you also have the option of using p-values. Most of the time, whenever you're now that you've gotten past the baby steps of hypothesis testing, when you're dealing with normal distribution, usually you'll just use p-values. So for these problems, that's what we're going to end up doing. But just keep in the back of your mind that you can use rejection regions just like you have in the past. Okay? Now, what we need to do next is we need to start talking about these hypotheses that we're going to write down, because they're going to look a little bit different than what we've done in the past, because we now have two means to deal with, not just one. So let's think about the null and the alternate hypothesis. Okay? So a null hypothesis, as you know, is H sub 0. Okay? What if we had two groups of people, or two populations that we're talking about? You can think about men versus women. You can think about old people versus young people. Anyway, there's two very large populations of people that we want to consider. Okay? Maybe my null hypothesis is that the mean of population 1 is less than or equal to the mean of population 2. Okay? What would this mean? I mean, how would this physically be the case? I mean, think about maybe the population. You have to label and know what you're writing down in terms of the hypothesis, right? So maybe mean number 1 represents, not going to start a war here, but maybe maybe it's the average height of men. Maybe the population 1 is all men in the city. Maybe the population 2 is all women in the city. So mean number 1, maybe we're talking about the average height or the average weight or something like that, or the average shoe size. Could be anything that can be represented by a mean. So let's talk about average height. So maybe population 1 is men or women, and maybe population 2 is men. So maybe we're saying the population of women in the city, that their height is on average lower, less than or equal to the average height of the population of men. Okay? Well, maybe somebody else comes along and says, I don't believe that's true. I'm going to write an alternate hypothesis that says that the mean population of 1 is greater than the mean population of 2. So if population 1 is women, and population 2 is men, the null or the accepted hypothesis would be that the average height of women is less than or equal to the average height of men. But the alternate research is saying the opposite's true. They're saying, no, I think in this particular case, now we're feeding some great hormones to the women. I'm just kidding. And their average height is actually now greater than the other population. I'm just using an example of height because it's easy to visualize, but these means can be anything. They can be two populations from a factory. They could be two different factories. Factory number 1 can be in China producing pencils, and factory number 2 can be in Los Angeles producing the same pencils. Maybe it's the same company. Maybe the mean is representing the length of the pencils, and we think that the pencil factory in China is making smaller pencils than the factory in Los Angeles, and this other guy comes along and says, no, I think the opposite's true. So you see how you can write hypothesis involving two population means, right? They can be anything you want, but you're generally comparing the two and seeing how they relate to one another. It's a very, very common thing to do. You have to kind of get through the basics of hypothesis testing, which is what we've done, in order to be able to understand this. But typically, we don't typically keep it written like this. And just, this is very easy to understand. That's why I wrote it this way. What this means is mean 1 is less than or equal to mean 2. And this one means that mean 1 is greater than mean 2. Now this is very easy to understand because I have something on the left side of the inequality and something on the right. And you can read this in terms of a sentence, right? But typically, you don't really write it like that. You usually, and this is how you're going to see this written in your textbook, as the following. You typically see it written like something like this. Let me switch to this color. The null hypothesis, for instance. Okay, visualize mu1, we'll just go ahead and put that here. Visualize, pretend this is an equal sign. Remember from algebra, you can move something over to the left and to the right. Remember how you do that in algebra? You can add anything you want to both sides of an equation, or you can subtract anything you want from both sides of an equation, as long as you do it to both sides of the equation. So pretend this was an equal sign here for a minute. If I wanted to move this mu2 over here, I would subtract mu2 from both sides. So I would subtract it from the left, and I would subtract it from the right. So subtracting from the left is going to give me minus mu2. And subtracting from the right, this minus itself is going to give me 0. Now, I told you to pretend it was an equal sign. That's because I know you all have some experience with algebra, moving things around on an equal sign. You can do exactly the same thing if it's an inequality. You can add or subtract anything you want to an equality as long as you do it to both sides. So this relation, mu1 minus mu2 is less than or equal to 0, is exactly the same as this. I know that when you read this, it doesn't seem like it's the same. But what it's saying is the difference in these population means is less than or equal to 0. It's the same thing as saying that the population of 1 is less than the population of 2. Because if you think about it, if this one was smaller than this one, then if I subtract them, I'll get a negative number, and that's what this is telling you. So you need to beat it in your head that something like this is exactly the same thing as this. And if you still don't visualize it, just mentally place this over here with a plus sign, and then come back to this if that's easier for you to remember. We can do the same thing here. The alternate hypothesis is mu1 minus mu2 is greater than 0. All we did was we take this guy, we do a subtraction and move it over. This is how you see it written down typically. So whenever you write your null hypothesis, you're going to write it usually as a difference of the two means. And you'll have, in this case, we have 0 over here, but you'll see as you do more problems that you may have a number over there or whatever. But usually in your hypotheses, you're going to see a difference in the two means, typically. So to give you another example of that, we have the difference with a less than, and then we have a greater than. So because of this guy, this is just like before, this is a right tail test. So this is going to be a distribution, a normal distribution with a right tail shaded region, just like we've done before. You may have another type of alternate hypothesis, or I should say null hypothesis and alternate hypothesis, that might look something like this. Mu1 minus mu2 is greater than or equal to 0. And then the alternate would then have to be mu1 minus mu2 is less than 0. And this is exactly the same as what I just wrote, except that the signs are flipped around. So because this points to the left, this is a left tail test. So you see, you don't flush what you learned before. The bottom inequality still points left or right, and it still tells you if you have a left or a right tail test. And as you might guess, if this guy points to the right, giving me a right tail test, and this guy points to the left, giving me a left tail test, then you most certainly can have a two-tail test as well. So something like that might be if I have mu1 minus mu2 is equal to 0, and then the alternate is mu1 minus mu2 would have to be not equal to 0, then because of this guy, this is a two-tail test. So we have a normal distribution that's going to govern these guys because it's a large sample. So we'd have a normal distribution with shaded areas in both tails. Now, the way you would read this in English is the mean of population 1 minus the mean of population 2 is 0. So if you mentally move this over to the other side, what it's saying is mu1 is equal to mu2. And what this is saying when you move it over is mu1 is not equal to mu2. I don't know about you, but looking at this is a lot easier for me to understand because I can think about two groups of people or two factories making pizzas. And the mean of 1 is equal to mean of 2, that's a null. And the mean of 1 is not equal to mean of 2, that's the alternate. This makes sense to me. Sometimes when I look at this, I know what it means because I've done all these problems, but sometimes when you look at this and equal to 0 and not equal to 0, it's not so clear. So if you're not sure, just mentally flip it over here or write it off to the side so that you have it clear in your head what you're doing. Because ultimately, this is exactly the same thing as this, and this is exactly the same thing as that. Okay? And so what we're really doing in this section is outlining a framework to show you when you might have problems when you have two population means, and you need to compare them. So we've had left tail test, we've had right tail test, and we've had two-tail test in this case. The only other thing that's different regarding these types of hypothesis testing compared to what you've seen before is the test statistic. Remember how we do it. You know, we draw a picture, we have a test statistic, we put in the sample data, because in order to do a hypothesis test, you have to grab some sampling of some kind. You put it into a test statistic, and then you see where that test statistic falls, and either you're going to reject or you're going to fail to reject. You have a similar kind of thing going on with p-values. Basically, you reject or you fail to reject based on the p-value. Okay? It all depends on that test statistic. Now, that test statistic in the past, you probably have it in buried recesses of your mind. It involved the mean, it involved the sample mean, it involved the standard deviation, it involved the number of samples that you had. So if you remember that test statistic from the past, that's basically what it was. This guy is a little more complicated because we now have two means running around, but the test statistic still gives us a number z back, and here's what it is. x1 bar minus x2 bar minus mu1 minus mu2 over big square root. If you remember, there was a square root on the bottom of the other test statistic also, s1 squared over n1 plus s2 squared over n2. And this is all under the square root on the bottom there. This is the test statistic that governs hypothesis testing involving two population means with large samples. In other words, 30 or greater samples, because in those cases we can use the normal distribution. The test statistic is giving us a number z. Don't get too worried or too scared of this complicated looking equation. I mean, ultimately you have two populations. So what you're going to do to test them, let's say you said, hey, population of 1 is greater than population of 2. Maybe you're talking about the height or something. So how do you think you're going to test that? You're going to go grab some data from population 1. You're going to go look at 40 people, let's say. And then you're going to go grab 30 or 40 people from population number 2. And you're going to collect and average their heights. Let's say you're studying the heights of these different populations. So this test statistic takes into account the average value of the data you get from population 1. It takes into account the average value of the data you get from population 2. It also takes into account the standard deviation, squared of course, of population 1, the standard deviation squared of population 2, and it also takes into account the number of samples that you picked from each population. So it takes into account exactly the same stuff that the original test statistic did when we had single mean hypothesis testing going on. So this should look real familiar. It's just that we have two different population variables going on. So there's more sampling, there's more data, but ultimately you just take that information, you stick it in here, out pops a single number. That single number is either going to fall in a rejection region or it's going to fall not in a rejection region. So the skeleton framework of these problems are still going to be like we've done before, but we need to read the problem a little more carefully, pull out all the information, put it in here, make sure we draw a picture to see where we're at, but ultimately the conclusion we draw is going to be exactly what we've learned before. So that's all I have for this section. It's more of an introduction section. Follow me on to the next lesson. I promise you, once I can read you a problem, show you what we're doing, then you'll be a lot more comfortable with it because the whole concept won't be so foreign once you can get a real problem in front of you. So let's go ahead and do that now in the next section.